that date is actually is a holiday for is a national holiday because of the Labor Day. If you have a difficulty um, to take the test during this date, okay, please let me know, because we try to find the date that suitable for you as well as the school, okay, so that our constraint is we need to run the test, or we need to do the test before the withdrawal, okay. uh, if you want to withdraw the subject, we need to do the test before the withdrawal week, which is in the week 8. Week 8 is, I believe, in the early of May. Okay, early of May. So that's why we need to do the test one before this. So if you have any problem to do this test, our first test in the proposed date, which is 1st May, so let me know, okay. So I will try to discuss with the other section whether is there any possibility to change or to have another date. Okay, if not, we assume that the date will be proceed as it is. Okay. That is about test. Second one, about the project. Okay, I think in this class I told you that in this course you will be have one assessment, one project assessment. Okay, and this project assessment is a group project. Okay, and in my case I will. What is the percentage covered in test one? I think it's a 20%. Okay, the percentage cover for the test one is 20%. Okay, it is same like what I have explained in the first slide. Let me check whether I can share you again the first slide. I mean the first slide, the slide of the first day. Yeah, this one. Okay. Okay, so the test one will be 20%, test two 20%. Okay, the assignment will be 10%, but the project is 10%. Okay, previously the project is 5%. It's very small, and because of this, some of you did not submit the project, probably because of the weightage is very small. So because of this, we change the project into the 10%, and the assignment or quiz will be 10% as well. Okay, so the project is a group project. Okay, last time when we are in the face-to-face mode, I request the project to be submitted by the report using a report or formal report. I think in this semester I will ask you to present the project as a video presentation. Okay, I will try to. I mean, this is my proposal. Okay, hopefully the coordinator can accept my proposal so that the project presentation, the presentation of the project will be in terms of video presentation. Okay, I will give you the details of the project probably next week. Okay, supposed to be a week before or 1 or 2 weeks before the semester break. Okay. Okay, so that is about the assessment, the coming assessment. Okay. Okay, so back to our topics in the chapter 3. Any question from the yesterday class? Or probably any question related to the example that you have learned or you have checked in the textbook? or you have tried some other example. Okay, the good thing about this textbook, okay. Oh yes, when I talk about textbook, I think you remember that in our test one, I mentioned that this is open book test. Okay, what meaning by open book test means that you can refer to any information from the textbook. Okay, so meaning that all information will be subjected from the textbook. Okay, for example, the properties, of course the equation, the properties, okay, the properties like, okay, like this example, okay, this K, for example, if you look to this example, the K for the glass is 0.78, the K for the air is 0.026. So in the test, this K will not given, okay, so you need to find the K value from the textbook, okay? Normally from the appendix, and you need to mention in your analysis from where you taken the K value or the properties value or the any value that you put in your analysis. Okay, so that is the purpose of the open textbook, meaning that wherever you takes, okay, wherever you takes information, whenever you take the information from the textbook, you need to mention from where. Okay, let's say you take some equation, so you have to mention this equation from what. Okay, for example, this is the textbook. Okay, let's say you want to take this equation. Okay, I'm not sure whether it is clear or not. Okay, if you want to take this let's say you want to take this equation and use in the exam or in the test, so you have to mention you taking this equation from equation this one 2.52a. Okay, actually if you go to the exercise, okay, some of the exercise explain that the equation is taken from the certain equation. Okay, I'm not sure whether it is mentioned here or not. Okay, like this. Okay, so it's mentioned here the equation taking from 256. So it's like it's mentioned the equation from where the original equation coming from. Okay, so that meaning by the open books mean you can take the equation from the textbook and you can take the properties from the textbook, especially in the appendix. Okay. Okay, so yesterday we stopped at the example of a series, thermal resistant at the series arrangement. Okay, but we still in the thermal resistant approach. Okay, in order to calculate the heat conduction analysis. Okay, so today we look into the other example of thermal resistant. Okay, so if you look to the previous or to the yesterday example, yesterday class, okay, the thermal resistant, the example or the problem of the thermal resistant that we are dealing is when the wall is in the series arrangement. Okay, so what happened if the layer in the parallel arrangement, okay, like this. So you may find this is a parallel arrangement. Okay, meanings if you have a heat transfer from this direction, okay, from left to the right, okay, so the heat facing a material with different thermal conductivity or different thermal properties. Okay, so there is insulation on the top and the bottom, meaning the heat will not pass through this area, but the heat will pass through this section where the thermal conductivity have a different value, K1 and K2. So how to do this? Okay, so you first you need to represent the system, okay, into the thermal resistance diagram. Okay, so this is the schematic. Okay, and this is the thermal resistance diagram. Okay, so you can see here the T1. Okay, the T1 is this temperature. Okay, we assume the T1 is in this surface temperature. Okay, so because of the different materials, so you need to represent the resistance into the parallel arrangement. Okay, so the K1, okay, the R1 is due to the K1. So what is the L over K1A 1, and R2 is due to the L2 K2 and A2. Okay, this is the conduction resistance. Okay, and the other temperature surface, okay, or T2 is on the right side. Okay, so at this condition, you need to assume that the temperature of the surface from the top side to the downside will be constant or similar. Okay, same goes to the T2. So in this case, what you need to calculate is, let's say you want to calculate the total thermal resistance. Okay, Q equals to delta T over R. Okay, so this is R total. Okay, this one from 1 to 2. So this R total is you can calculate by combining the resistance due to the parallel arrangement. Okay, like this. I think a similar approach when you are dealing with electrical calculation, when you have electrical resistance in the parallel arrangement, then you need to find the equivalent resistance, okay, by using the same method or same approach. Okay, so you might thinking that where is the parallel application in the heat transfer. Okay, I think you know this kind of um, system. Of course, our wall is consists of a brick wall and cement composition. Okay, cement composition. So in order to consider, of course, this kind of system, you may have a different K. Okay, that means this brick have a different K like this cement. Okay, let's say this is K for the brick, this is K for the cement. Okay, so this means in order to study the total resistance of this particular wall, okay, if we want to get more details calculation, then we have to consider the K cement and the K brick, which is slightly different but not too much. Okay, so in this case, what you can do is, if you see the cross section of this wall, for example, okay, the cross section, okay, so you may see cross section from this view, okay, so you may see that you have the wall, you have the brick, and then you have the cement, and then you have the brick again, okay, then you have the cement, and this section will be repeated towards how tall or how high the wall, okay, wall height. Okay, so this is that you need to consider that if you want to study the temperature from this side, let's say this is your inside, let's say this is your outside, okay, so if you are considering this thermal resistance, so probably you may have one resistance due to the brick, one resistance due to the cement, okay, and then again resistance due to the brick, and then resistance due to the cement, and this one will be repeated, okay, whether you want to calculate at the specific wall height or you want to calculate for the whole wall height, okay, so this is where the application of parallel resistance need to be considered in the heat conduction analysis. Okay, so if you have multiple rings, like in this case you have the parallel and you have a series, okay, so you can simplify the system or the multiple arrangement, okay, by drawing a simple or by simplifying the resistance into the thermal resistance diagram, okay, so in order to solve this kind of example, okay, so if you have this kind of example, so you need to draw the thermal resistance, okay, for the K1, for the K2, and also for the K3, okay, okay, like this. So here you have a 3 different material, okay, so you have a 3 different material. So K1 you have R1, K2 you have, okay, K1 you have the R1, K2 you have the R2, and then K3 you have the R3, okay, so basically the resistance between the R1 and R2 is in the parallel arrangement. Find the resistance, the equivalent resistance for the R12, okay, before you add R3, because the R3 is a basically series resistance, okay. So still you use the same general conduction equation resistance, Q equals to delta T over R, but the R calculation will be depending on how your thermal resistance diagram will be, okay. So this one R, so the R total calculation, this R total calculation depend on thermal resistance diagram, okay. So this is your schematic, this is your thermal resistance diagram. If you look to the textbook, some of the example did not draw the thermal resistance diagram, but in my case, okay, I think they have, okay. I think thermal resistance diagram is a good step, okay, in order good step to include in your analysis, in order to give a clear description on how your total resistance calculation will be obtained. Okay. 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 Any question? Generalized thermal resistance. So you need to understand the I think on there are only two arrangements, series and parallel. Okay. So whenever you find the series arrangement, you just adding you just add the resistance directly. But if you use the parallel resistance, then you have to find the equivalent resistance. So this one R12 is the equivalent resistance. Okay, so R12 this is equivalent resistance for combination R1 and R2 due to the parallel resistance. Okay, you can look this kind of, I'm not sure whether there is example of resistance or not. If you, let's check some example. I will not go to the example. I hope you can go through this example whenever you've got a free time. I just want to show you what is the example that related to the series arrangement. Yesterday we learned about the 3, 4. Yeah, this one term generalized. Okay, example 3, 6. Okay. Okay, example 3, 6. If you look to this one, so in fact, the combination of example in 3, 6 will be a bit complex. Okay, because it is dealing with how many materials here. You got the foam here, you got the plaster, which is a cement, you got the bricks, and you have the convection in the outside and inside. Okay, so Ri is due to the convection, R1 due to the foam, R2 is due to the plaster. For that particular section. Okay, R3 and R4 and R5 is basically okay, if I can label here, this is the I, this is a 1, this is the 2, this is the 3, this is the 4, this is 5, this is a 6, and this is the 7. Sorry, there is no 7, there is O here. Okay, O, R0. Okay, this is Ri. So you can see it's the same material, but because of the arrangement is different, then they divided into different resistance. So how they divided, they will put I think like this. Okay. Okay. This is a good example in order to understand the combination of thermal resistance from series and parallel. Okay. So I, 1, 2, 6 and O is a series, but 3, 4 and 5 is the parallel arrangement. Okay, so they only focus in this region only. Okay, so they only focus in this one, and then they multiply how many this section will be found if you have a certain height of the wall. Okay, so they don't study the whole wall, because this is another way to do that. So that, because this one is this section will be repeated. Okay, will be repeated as the wall is increased. Okay, the height increase. So you just need to multiply how many the section will be counted, okay, to complete a whole wall, okay. So this is a good example if you want to understand the combination of series and parallel. Okay. So next one we go to the cylindrical coordinate. Okay. So in the chapter 2, you remember that on top of the Cartesian, you also need to do the conduction analysis under cylindrical and spherical. Okay. So when we talk about the cylindrical coordinates, okay, so what we need to understand that the temperature variation, okay, the temperature distribution, okay, the temperature variation, okay, across the cylinder will be vary as a function of radius, okay. So in this case, our focus is in the radius axis, r axis, okay. So one dimensional analysis for cylinder, okay, focus on r axis, radius axis. So we will not go to the axis on the length of the cylinder, okay, because we assume the distribution of the temperature of the tube will be same, will be identical, okay, in every section or in every part. We only need to consider the temperature distribution in the radius direction, okay, radius direction, okay. So if you look to this particular cross section, okay, let's say I want to draw, okay, I need to find a new blanks, okay. So let's say this is for cylinder, okay. So let's say this is your so this is a quarter of the cylinder. Is to draw a straight, okay. Let's say this is the okay. Let's say I put another layer of okay. So you have this one R1, we have R2, we have the radius of R3, okay. So I'm not drawing the other quarter because I assume that the cylinder is in the symmetrical shape, okay. Of course, it's in the symmetrical shape. We only draw the quarter section of this cylinder, okay. So in case of the cylinder, you also got the term okay, thermal resistance for the cylinder. Okay, where is the slide? Okay. Okay, using the concept of heat conduction equation, okay, same approach. Okay, if you look to the textbook, okay, I'm not really go into details for the derivation. Okay, so if you look to the textbook section 3.4, okay, using derivation of conduction resistance for cylinder as in section 3.4. Okay. Okay. Where is section 3.4? Yeah, this one. Okay. So this is our original equation. Okay. After you simplify, okay. After you simplify from the long equation of the cylinder, you actually it is combined three axes, okay, radius, length, as well as the height, okay. But because of the boundary condition, okay, because of the boundary condition maintained at a constant temperature T1 and T2, no heat generation, thermal conductivity constant. So you simplify the equation, this simple, okay, this short equation, okay, and then you do the integration for this particular, same thing like the Cartesian. So you will get with this limitation of the R equal to R1, TR1 equals T1, R equal to R2, and TR2 equals to T2. So you will get the heat conduction resistance for the cylinder is this. Okay. So this equation in terms of the general equation delta T over R. Okay, same like the plane wall. So you may find the R now is actually due to the ln R2 divided by R1 divide by 2 pi Lk. Okay, so R for the conduction in case of this will be ln R2 divided by R1 divided by 2 pi Lk. So this is how this. Okay, in here in my slide I did not explain how we got this R cylinder for the conductor. Okay, but when you go to the textbook there is a pretty long explanation from how you can get the R cylinder in terms of conduction in this particular form. Okay, so this is the important part for the cylinder. Okay, so when we back to our equation, okay, let's say this is the let's say I assume this is the cylinder, hollow cylinder. Okay, and then you have some insulation here. Okay, so basically here you have the let's say hot water. You are using this cylinder for transport hot water, and the outside part is the ambient. Okay, at 30 degrees Celsius. Okay, so here you have your H naught. Here you have the H inside area. Okay, so if you look to this particular section or particular problem, so you may have, okay, if I can plot the resistance in terms of the thermal resistance, okay, so if this is your temperature inside, and this is your temperature outside, T naught, which is at 30 degrees Celsius. So first you will pass through a resistance due to the convection. Okay, and then after this section, you will pass through a resistance due to the pipe. Let's say I said it, this is a metal pipe. Okay, and this one probably the insulator. Okay, so the first resistance is due to the convection. The second resistance is due to the metal pipe. Okay, same goes here. The resistance due to the third layer, which is resistance due to the insulator. Okay, and finally resistance due to the convection, but on the outside part. Convection outside. This is convection inside. Okay, so for this simple system where you have the pipe and the insulator, okay, by exposing to the environment, okay, and you are using hollow cylinder, you basically are dealing with 4 series of thermal resistance. Okay, so how to calculate this? Okay, so basically you can calculate R convection for the inside equals to 1 over HA, same like the same like in the plane wall. Okay, second R metal. Okay, so this one is based on the equation, okay, which is ln R2 divided by R1 2 pi L in K1. So this is a K pipe. Okay, K pipe. Okay, the third one, R insulation, equals to ln R3, because the insulation is between R3 and and R2. So R3 over R2 divided by 2 pi L K for the insulation. Okay, and the last one, R for the convection outside. Okay, same one H naught divided by A. Okay, you have to understand that under plane wall, the A is basically the cross section, but for the case of cylinder, the A is the A cylinder at section at radius given. So this means for this one, the A is a what is the cross section? 2 pi R1 times L. Okay, for this. And for this A, the A here is a 2 pi R. Because of this is the outer part, so this is R3 times L. Okay, or sometimes you can put it in the diameter pi D3L. Okay, same thing. Okay, so this is the only difference between the plane wall and the cylinder, because the different in terms of the effective area exposed to the convection. Okay, so back to the lecture slide. So you can see here, that's why in this particular calculation of resistance due to the convection, you have this one 2 pi R1L. Okay, so basically this one representing the area of the cylinder at the radius given. Okay, this one for the R1, this one for the R2. Okay, so this is a cylinder. I think this is air cylinder outside. This is air cylinder inside. In. Okay, sorry for the bad handwriting. Okay, I hope you can understand the calculation. Okay, so this is for the cylinder. How about sphere? So same thing, using the same concept of the spherical coordinates. Okay. So for the spherical coordinate, the only difference is the conduction due to the spherical and the area of the spherical. Okay, so let's say this is your spherical system or spherical shape geometry. So of course in the spherical you may keep some fluid inside. So because of this fluid you have the convection in the internal part. Okay, so next one is the, so this is the wrong one, this is not cylinder, this is sphere. Okay, so sorry for the typo error, this should be R spherical. Okay, so this is the first, this is the second, and this is the third one, R convection outside. So if you look here, the R conduction for the spherical is a bit different compared to the cylinder. So how this equation is derived? So using the same hot heat conduction equation. Okay, so if you look, this is for the spherical. Okay, equation starting from equation 340. Okay, so we repeat the analysis for the spherical layer. Okay, performing the integration of equation 336. So you will have the conduction resistance for the spherical is this form. Okay, so if you want to calculate the R total for the spherical, so this is equals to the R convection inside plus R spherical plus R convection outside. Okay, so same thing 1 over H I A. Okay, this is I. Okay, plus R2 minus R1 divided by 4 pi R1 R2 K plus 1 over H not A A. Okay, I can put it, this is AI, this is A naught. Okay, so what is the AI or A1? AI equals to, what is the area for the spherical? You remember? I think 4 pi R I to the power of, R1, Ri to the power of 2. Okay, and A naught is a, yes, correct. Thank you, Ayman. 4 pi R O to the power of 2. Okay. So like the cylindrical, the difference is due to the area and also the conduction resistance. Okay, the rest is the same. Okay, the concept also same. Okay. Just to, I don't know whether you have a see example of the resistance, but if you look to the example, okay, for case of spherical and cylindrical, most of the cases we will find the series arrangement. It's quite difficult to find the parallel arrangement. Okay, which I think that there is a limited parallel resistant arrangement under case of cylindrical and spherical. Okay, the only thing that you might consider parallel if you have effect of convection and radiation. Okay, I don't know whether I have this kind of example here. No, let's see. Where is the, okay? Okay, let's say I want to consider the same. Okay, let's say I consider a cylinder. Okay, so this is the center part. Okay, let's say we only have one layer, one hollow cylinder. Okay, so you have R1 here, and then you have the R2 here. Okay, so this is the ambient. Okay, at 30 degrees Celsius. Okay, so basically if you want to draw the resistance, okay, assuming this is a cylinder, hollow cylinder, okay, hollow cylinder, okay, at room condition. Okay. So in the ambient, okay, in this ambient condition, normally when we say that under normal condition, there will be effect of convection. Okay, and radiation. Remember in the chapter 1, okay, when any object or any system, if the temperature above 0 Kelvin, there will be a radiation heat transfer. Okay, so in this case, we assume that convection and radiation at surrounding need to be considered. Okay, if you look to this problem, the convection only considered, but not radiation. Okay, probably because of the assumption say that neglect the effect of radiation. But in this example, or in this case, so this case, radiation need radiation heat transfer need to be considered. Okay, okay, how? Okay, so if you draw the thermal resistance, okay, if you draw the thermal resistance, okay, let's say I try to extend this. Okay, so this is your schematic diagram. So this is your schematic diagram. The next one, your thermal resistance diagram. Okay, so starting from this one, T inside. It's quite difficult to put a blue one. No. Okay. Okay, T inside. Okay. So this is the T inside. Very sensitive. Sorry guys. T I. So outside is a T naught. Okay, and this is the K for the pipe. K for the pipe. So here you have the HI and you have here H naught. Okay. So if we draw the thermal resistance, okay, first I need to draw the bond. A different color, is it? Sorry. Okay. How to draw a straight line? It's not easy. Okay. So this is the outside. Okay. So so this one is your T outside. Okay. So this is the temperature between the temperature at the surface inside. This is the temperature at the surface outside. Okay. Okay, so the first resistance is due to the convection, R convection inside. Okay. Convection inside. Okay, next one due to the R pipe. Okay, R pipe. Okay, because of here you have both effect, convection and radiation. So what happened here is you need to replace with the parallel arrangement. Okay, so this is R due to the convection. R due to the convection. R due to the convection. And the other one is R due to the radiation. Okay, so you have to find that the equivalent resistance due to the convection and radiation by using a parallel approach. Okay, so what is the R convection? Same thing, R convection equals to 1 over H O divided by A outside. Okay, and what is the R radiation? Equals to 1 over H R, H by radiation, A naught. I'm not sure whether you are um, uh, I'm not sure whether you're aware about the radiation also can be expressed in terms of heat convection coefficient radiation. HR is a heat transfer coefficient of radiation. Okay, so if you're not aware, this HR can be calculated in where is the textbook? Using the equation in the chapter 1. Okay, if you go to the chapter 1, okay, under part radiation. Okay, I think in equation where is the radiation? Topic radiation.
Page 28. Sir.
28. Oh, okay, 28. Yes, this one. Okay. Yes. Section 1.8 radiation. Okay. So if you go a bit down, yes, this one. H radiation. H radiation here can be calculated from this equation. Okay. H radiation equals to emissivity times Stephen Boltzmann times surface temperature plus surrounding temperature times T surface to the power of 2 plus T surrounding to the power of 2. Okay, of course, I don't think you can remember. I also not remember. So that's why you can refer to this equation. Whenever they ask you to consider the radiation heat transfer convection, heat transfer coefficient due to the radiation. Okay, HR, H radiation. Okay. So in here you need to have information of emissivity surface temperature and surrounding temperature. Okay, once you know this, you can calculate HR, and then go back to our step. Okay, so you need to find the corresponding area of the outer surface for the cylinder. Then you can find the equivalent resistance. Okay, the equivalent resistance R of the convection plus radiation. I don't put plus, you will confuse it. R convection radiation will be R convection multiplied by R radiation divided by R convection plus R radiation. Okay, same like R1 and R2 equivalent temperature, equivalent resistance. Okay. Any question? Where is? Okay. So okay, this is an example of problem. This is example. You want to try this example, problem 381. I think this is the old textbook, 381. If you go to the new textbook, it should be steam at 230. I think 384 or 5. Any questions so far? You want to ask? Probably you're not very clear about how to use it.
That I want to ask something. The radiation pipe, do we need, how do we know that we need to include radiation pipe?
Okay. Normally when the problem's given, okay, if normally what I always do is I compare the H value under natural convection. Okay. In this case, you need to understand the H value of convection coefficient. Okay, because both will calculate H. Okay, both will calculate H value of convection. Heat transfer coefficient H value. Okay. To assist this assumption, you need to understand what is the typical value of H. Okay. I need to show you in the chapter 1. Okay. In the chapter 1, when you have the heat transfer convection coefficient. I think in 1.7, section 1.7, when you talk about convection, there is a table show the typical value. Yeah, this one. Okay, table 1.5. Okay, a good question actually. Your friend asking how to know whether you need to neglect the radiation or not. Okay, this one. This table. Okay, this is a typical value of H. Okay, this is under free convection. This is under free but liquid. This is under forced convection. Okay, and this is the forced convection for the liquid. I'll always go to this the first for value. Okay, this one. Okay, Okay, when we dealing with a system, okay, we always see that the system is located at the ambient condition, and the ambient condition will be have some H value. Okay, for example here, I want to find one example. In fact, okay, this one. Okay, so this problem, for example, okay, whether you really want to consider radiation or not. Okay, so if you look to this problem, the steam at 230, and then with the inner radius, inner diameter 9 and 10, and then the environment at 13 degrees Celsius. Okay, and then the properties given and the heat transfer coefficient 170 and 30. Okay, 170 watt per meter squared Kelvin for the inside and 30 for the outside. Okay, so my rule of thumb normally, what I will say that if your value is below than 20 watt per meter squared, or 25, in this case 25, okay, 25 is the typical value of free convection. Okay, I not go to 2, I go to the highest for the free convection of gas. Okay, gas here is also meaning air. Okay, so anything below 25, that means you need to consider the radiation. Okay? Because above 25, okay, the forced convection will be dominant. Okay, actually you, when they explain about whether you want to consider radiation or not. Okay, I try to find some example on convection so that it is clearly indicate. Sometimes you can forget, sometimes you can neglect, sometimes you cannot. Okay, here for example, okay, this heat loss from a person. See what is the value of convection radiation? Convection coefficient 6. 6 is very small compared to 25. So because of this value is very small, the effect of radiation is quite significant. Okay, but if the H value is greater than 25, so the effect of the H radiation can be neglected. Okay? So this is a way of how the effect of radiation. Okay. We try to find some description on how to neglect the radiation. I cannot find it. I cannot find any example here. Let's say we go to some example in the radiation, in the conduction resistance. Okay. Try to find some equation problem of conduct that neglect the radiation. Okay, so my rule of thumb, normally I compare the H value. Okay, but of course you need to calculate it. No, this one. But at some cases, if you don't want to calculate, you can neglect. You can neglect the value. Just add it is. I mean, you can say that the effect of radiation is neglected. Okay, you look here. Okay, this example, a composite wall. See the H value. The H value outside and inside. The H value 10 and the H value 25. Okay, see the assumption? Heat transfer by radiation is negligible. Okay, well, because of the value is low, then I mean, if it is low than 25, at least at one, where is one? One is the inside. Okay, so actually you should consider radiation in this part. You should consider radiation plus convection in this part. Okay, but here they just simply say that the heat transfer by radiation is negligible. Also can, because you want to concentrate the effect of the convection. But the true analysis, you need to consider if the convection coefficient is less than 25. In this case, probably the negligible term is correct, because it is nearly 25 and below. Sorry, 25 and above. Okay, because you have to understand that the resistance, okay, the resistance calculation is 1 over HE. So if this H is increased, okay, so the value of resistance will be small. Okay, as H is increased, the R value will be small, correct? The higher the lower the R, the greater the effect. Okay, because this will be related to the Q equals to delta T over R. Okay, if R is small, Q will be increased. Okay, we want to have a bigger R in order to control the heat transfer. Okay, in order to control the heat transfer, we want the small R. But if we want to increase the heat transfer, we want the R to be small enough. Okay, as low as possible. Okay, depending on what you want to apply, what you want to target. You want to increase the heat transfer or you want to reduce the heat transfer. Okay, because the resistance is related to the heat transfer calculation. Okay. Okay, I hope I answer your question. First, you compare with the H value. Second, if it is time not permit, normally in our test or example in exam, we always neglect the radiation unless it is stated that you need to consider the radiation. Okay. Okay. I think in this case, I think this problem is quite similar with the example in the textbook. Okay, this is steam insulated 170. I think if you go to the textbook, yeah, this one. Okay, heat transfer in the, yeah, insulated steam pipe. Okay, so if you look to this problem, quite same. You have the temperature inside 330. You have the pipe from the cast iron. You have the internal diameter, external diameter. You have the insulation using a glass wool at K 0.05. You have the surrounding temperature at 5 degrees Celsius. You have the outside. Okay, here they combine the convection and radiation. We already combined the heat transfer convection coefficient. Okay, by considering natural convection and radiation. So you don't need to calculate separately. Okay, and the inside is 60. So yeah, this is the schematic. Okay, here they draw three-dimensional 3D system. But if you can draw two-dimensional, is enough for showing the problem. Okay, so this is the schematic diagram. This is for the thermal resistance diagram. Okay, so you calculate the area, you calculate the thermal resistance in each section, and you find the total resistance, and then you calculate the heat rate based on the difference in temperature from inside to outside. Okay, based on the total resistance. Okay. Okay. So you can try this problem by comparing with example in the textbook. Okay. Okay. Next one, I need to explain about the contact resistance. Okay. Not very important, because some value of contact resistance will be very small compared to the resistance due to the solid object, but at some cases they give you a significant impact to the temperature distribution. Okay, so what is the contact resistance? Contact resistance is whenever you are combining two solid object or two solid metal or non-metal, and then there is some action, contact resistance between these two objects. Okay, let's say you have this metal A, this is metal A, this is metal B, this is metal B, this is a metal A. Okay, so you want to combine this, whether you want to combine using a welding process, or whether you want to combine using a pressing compress, whether you want to combine using a glue, or whether you want to combine using what? Pressing, welding, okay, any kind of adhesive. Okay, so you can combine, but there will be some contact resistance exists. Okay, so meaning that if you want to plot the temperature variation from left to the right, okay, let's say from here x1 to x2, this is x1, this is x2. Okay, so what you found is there will be some temperature drop at the contact between the metal. Okay, if this is x1, 2, I put it x1, 2. So here there will be a temperature drop. This is a temperature drop due to the contact resistance. Okay, why? Because actually when you combine two different object of metal, there is possibility of another material within these two metal. Okay, so if we can study in terms of the micro scale, okay, let's say you do some microscopic view for this particular metal A and B, you can see there will be some what is this? What is the, of course, when you see how come this can be happen, actually when you go into the microstructure view, okay, the cross section is not actually in the straight line. Okay, there will be some defect in terms of the surface roughness. Okay, and because of the different surface roughness, when you combine, there will be a pockets. Okay, or sometimes they call it air gap. So this air gap, okay, or this air pocket is basically introduce thermal resistance. Okay, introduce resistance to the heat to move freely. Okay, if it is a solid, there is no air pocket, that means the heat can transfer easily from metal to metal. But because of there is an air gap, okay, this create some deficiency in the heat transfer. Okay, so when you got direct contact metal to metal, so the heat can easily transfer. Okay, but if there is no direct contact where you get the air pockets, air gap, this creates some extra layer, which basically you are introducing air as a layer of thermal resistance. Okay, you don't need to calculate, but you need to consider in your calculation at some cases. Okay, so how to consider this phenomenon? Okay, so the thermal contact conductance or thermal contact heat transfer coefficient, thermal contact coefficient. Okay, so HC. Okay, I can say HC here is a thermal contact heat coefficient. It's a coefficient. Okay, so you can calculate this if you know the heat transfer and you know the area of that particular section and the temperature difference. But it's not really easy to calculate this value. Okay, because sometimes this value is a bit complex. So what they use is they use some table. Okay, some study have done before, and this study is plotted into a table, and you can see here by using table 3.2 you can find the H value. Okay, if you know the metals, the pair of the metals, the surface condition, the roughness, the temperature, and the pressure. Okay, so if, let's say for example, if you are using stainless steel and aluminum, okay, where the surface roughness is within this range, okay, the temperature of the joining at 20 degrees Celsius and the pressure to join the metal is either 10 or 20, so the H value, the corresponding H value will be either these two. Okay, I can say that the value is very limited to the certain condition and the certain material. Okay, but it is good to assist you that this value might have effect to your calculation of the thermal resistance. Okay, so the calculation will be RC. Okay, let's say you want to consider the RC. Okay, okay, let's say we consider two layer. Okay, two layer of metal. Okay, let's say this is metal A, this is metal B. Okay, this is the surrounding, this is inside, this is the outside. Okay, so where you have the HI and this you have the H outside. Okay, if contact resistance negative, your thermal resistance diagram will be consists of 4 resistance. This is Ri, R due to the convection. This is R conduction due to the metal A. This is R conduction due to metal B. This is R due to the convection outside. Okay. However, if you need to consider the contact resistance, if contact resistance need to include, okay, so now the temperature resistance become phi resistance. This is small. So same, this is Ri, this is R0, this is Ra, this is Rb. So you have here R contact between A and B. Okay, so how, okay, you know how to calculate Ri, Ra, Rb and R0, but how to calculate R, C, A, B is basically using the slide here, this one, delta T interface divided by HCA. Okay, so delta T between AB divided by HCA. So how to find HC? So HC is normally from the table. From table 3.2. Okay. Where is my cursor? Okay, from this one, table H2. So this value HC. So what is the area of the section? The area is the same. This one, the area. Okay. The area. So this is the area. Okay, if it is in the. So this is the area. Okay. So what is the temperature? Different is the temperature between surface A and surface B. Normally, they will give you the difference in the temperature, very small, but not too much compared to the temperature on the other side. Okay, so the tricky part is how to find the HC, because if you look to the HC table, you need to find the HC depending on the surface condition, depending on the surface roughness, temperature, as well as the pressure of the contact. Okay, but this is if you want to consider. But again, sometimes because of the condition is not given, we always neglected. Okay, let's say if you go to some textbook. Okay, see here, thermal contact resistance at interface is negligible. So this means they don't consider the thermal contact resistance. Otherwise, you need to find how much the pressure, how much the temperature at that particular interface, how much the in fact the material also did not provide the table, completely provided. So to make it short or to simplify the solution, we neglect for the first calculation. Okay, so that's why whenever you study the example in the textbook, you need to understand every single assumption. Each assumption basically have a reason why this assumption used. It's not simply that, okay, this assumption can use in all analysis of heat transfer. Not as simple as that. Okay, every assumption used to assist and simplify the assumption so that you can get more accurate, but in a simple way. Okay. Okay, we back to the slide. Okay, so this is another example. They say you want to consider, you want to calculate the total resistance of the, what? This is, I think this is a boiler wall where you have the flame, you have the structure fabric, and you have the cool air. Okay, so because of there is a contact resistance between the insulation. Okay, so you have this contact resistance. Okay, this one. So you need to consider in your calculation if required. Okay, not necessary, not compulsory, but sometimes it is required. Okay, okay, see this example. Okay, not example, actually it's in the problem. Okay, so it's mentioned here, the ground surfaces are pressed against each other with a pressure of 20 atm. The bar are enclosed an insulation sleeve, and then what? The top and bottom surface of the two bar system are maintained at 150 and 20 degrees Celsius. Okay, so here you need to consider the contact resistance for this aluminum bar. Okay, so aluminum with aluminum. Okay, so same material, aluminum. So basically you can use this one. Okay, aluminum. What is the pressure? 20 atm. Okay, 20 atm is close to 2 megapascal. Okay, the problem say it is 20 atm. How to change 20 atm to megapascal? 20 atm is close to 20 bar. And 20 bar is near to 2 megapascal. So this value is within this range. Okay, so you can take the 11,400 value of HC under your analysis. Okay. Okay, so this is just okay. So that's all for the thermal resistance. Okay, so we cover about the plane wall yesterday. Today we cover about the cylinder. We cover about the spherical. Probably we don't go to the example. You can look the example of spherical in the textbook here. If you go to the example 3.7, this is a heat transfer thermal resistance using a spherical container. So you can see how the calculation. Here. So there is calculation of H radiation. In fact, this one considering the effect of radiation and effect of convection. And they used to find the equivalent resistance due to the radiation and convection. Okay, so you can go to this example to compare how they calculate the combination of convection and radiation in terms of parallel arrangement. Okay, and also we cover about the contact resistance, not very sometimes considered in the calculation. Okay, so the next topic of the conduction resistance is the fins. Okay, extended surface and fins. I will cover this in the next week's class. Okay, any questions so far? Any question? Please have time to do some example, understand the example in the textbook. I think the example in the textbook is very clear in order to explain to you how to apply the thermal resistance starting from a plane wall. I think plane wall as in the example 3. Yeah, 3.1. Okay, 3.1 is a simple thermal resistance. Then 3.2 another thermal resistance, but very simple layer, only one layer. And then 3.3 when you have a multiple layer, still in the series. 3.4. Okay, when you have contact resistance, you can go through this example of contact resistance. 3.5 not very important for the topics, but you can use as your understanding to strengthen your understanding. 3.6 is a combination between the series and parallel arrangement. Okay, it's very good, this example. And 3.7 and 3.8 for the case of spherical and cylindrical. Okay, I will not go to the example. I think if we have time later in the next class, we will do some example, or probably I give you some assignment related to the plane wall, and then cylinder, and then spherical, in order to strengthen your understanding. Okay. Okay, so test 1 cover until test 1 cover until thermal resistance. Okay, thermal resistance, is it? Let me check. I think thermal resistance, if I'm not mistaken. This one, not many section have reached this topic yet. Okay, I think this one is not in your test 1. Your test 1 until here. Okay, until thermal resistance. So that's why you need to understand all these different coordinate, Cartesian coordinate, cylinder coordinate, as well as spherical coordinate. Whenever you are dealing with the heat conduction analysis. Same goes to the chapter 2, okay? Because in the chapter 2, we also introduce you in the Cartesian, cylindrical and spherical. We only do some example on the Cartesian, but we not cover the example in the cylindrical and spherical. But this is still important. You can use the example of cylindrical and spherical. I'm not sure whether it is given. I think in the chapter 2. Let me check. In the chapter 2, since it is covered in your test, so you need to understand how the derivation of one-dimensional analysis for the case of cylinder and for the case of spherical. Where is it? Previously, we discussed about plane wall. Where is it? Yes, this one. Okay, 210. Okay, you need how they got these terms from the long equation until this equation. This is for the plane wall or Cartesian. For cylindrical, you need to go to this to the example of 215. Okay, this is for the cylinder. Okay, so look how from the long equation you are using this simplify equation. Okay, and for the spherical, this one. Oh, what happened suddenly? Okay, this is for the spherical coordinate. Okay, you can see quite slightly different of the mathematical formulation. Okay, so so for your test, it is covered chapter 1, chapter 2, and chapter 3 until thermal resistance. Okay, but don't worry, it is open book. You still have this example for you to understand. But again, my advice is do not, please don't please don't understand the example during the test. You will not understand the example in the very short time. Okay, for example, you need to understand why the assumption written here. Okay, you need to understand each statement in the textbook. Okay, so that it can assist your understanding. Okay, to solve the problem related to the heat transfer, whether it is cylindrical, spherical, or Cartesian coordinate. Okay, I think that's all to answer your question. Okay, so with that, thank you very much.